Can you see my screen now?
Not yet.
Yes.
We can see your screen now.
Great,
Yeah,
thanks.
everything is fine.
All right, so we know bioelectronics are playing increasingly important roles in advancing healthcare, as the previous speaker, Professor Wu Bai, has presented. And here in the first row, I'm showing some commercially available bioelectronic devices, 3 different categories. First one is a wearable health tracker that many of us wear on a daily basis. It's loosely strapped to our wrist to measure our physical activities. The second example is a silicon-based rigid probe for neural sensing and stimulation. And third example is a surgical tool, the mapping catheter for mapping cardiac activities to assist the cardiac surgeries. And while these devices are functional, they are stiff, rigid, and apparently there's a clear mechanical mismatch between these rigid devices and the soft, curvilinear, and dynamic soft tissues in biology. So to mitigate this mechanical mismatch, we have seen the transition between from rigid electronics to soft and even deformable bioelectronic devices. Shown in the bottom row, we have electronic tattoos that can be attached to our skin in a mechanically imperceptible manner, and also enables new functions such as measuring skin deformations or sweat analysis, which are not possible using rigid electronics. And we also have soft neural probes that are less invasive, more suitable for chronic use. And the last example is a soft deformable balloon catheter with electronics integrated on them, which can expand to better conform to soft deformable tissues. This one is developed by our moderator, Professor Mengdi Han. So we see that this transition from rigid bioelectronics to soft and deformable ones open up a lot of exciting opportunities. It means better interface between bioelectronics and soft tissues, more effective diagnosis and therapy in a safer manner. So with all these advantages, then how can we develop stretchable bioelectronics? We know conventional electronics are manufactured using standard integrated circuit microfabrication technologies, which are planar and using mostly rigid materials. And in order to develop stretchable electronics, we have different strategies. In our lab, we focus on both using kind of structure designs, applying structure designs to existing rigid materials. Showing the first 2 examples, we can leverage in-plant stretchable structures and out-plant stretchable structures to give intrinsically non-stretchable materials some device-level stretchability. And then in the last example, I show that we can also use intrinsically stretchable materials. In this case, gallium-based liquid metal to develop intrinsically stretchable structures and devices. The first example is how we use in-plant stretchable structures such as serpentine interconnects to develop stretchable microneedle electrode arrays for intramuscular EMG sensing. Microelectrode arrays, or MEAs, is a very commonly used technology platform for kind of electrophysiological sensing and stimulation. So we have 2D planar MEAs, and if you want to access the interior of tissues, we have 3D, 2.5D, and 3D MEAs. If it's on rigid electrodes, 2 and 5D, and if it's on flexible substrate, for example, polymeric substrate, we can have flexible MEAs that can penetrate surface tissues. However, look at our organs and tissues, some of them are highly deformable, as shown here. So if we want to measure, for example, intramuscular EMG signals from our cardiac or skeletal muscle tissues or on our bladder, we need to make sure that the microneedle electrodes are able to conform to these tissues. And we also want to have individual adjustability to the electrodes. And we also hope that each individual needle can be customized to reach targeted regions inside the tissue. And finally, we want to have a scalable fabrication process for that. So here's what we have developed. Here we have an array of rigid microneedle electrodes with their tip exposed for targeted sensing and stimulation. And how can we make rigid microneedle electrode stretchable. We use serpentine interconnects, which is the commonly used structure design in stretchable electronics. Each microneedle is electrically connected to a serpentine interconnect. Then they're connected to external electronics. And the microneedles and the serpentine interconnects are bonded covalently to a stretchable elastomer substrate, so that when we stretch, the serpentine interconnects can deform, rotate, implant, while keeping the needles rigid and intact. So that's the idea. And we fabricated these stretchable microneedle electrode arrays using a hybrid method combining laser, micromachining, photolithography, and transfer printing. The result of this process is that we can make this polyimide-based microneedle coated with gold to make them conductive. And these microneedles and the serpentine interconnects are bonded to a highly stretchable EcoFlex substrate. And because of the covalent bonding, the strength, the adhesion is very strong, so the needles can deform without delamination. And more interestingly, because each microneedle geometry is determined by the laser micromachining process, so we have complete control over the dimensions of individual needle, which is advantageous for targeting specific regions in tissue, for example, different depths. And another challenge we overcame was how can we make sure that we only expose the tip of the conductive microneedle. The key idea is that we use parylene for encapsulation, but then we etch the parylene at the tip using a copper hard mask. Eventually, we need to etch the copper at the tip. And we found that if we use the liquid copper agent, it's going to spread and prevent us from only etching the tip. So we developed a agar gel-based etching system, basically immerse agar gel into copper agent, so that when we dip the tip of the needle into the gel, we only etch the copper at the tip because of the large viscous force inside the gel. So this allows us to kind of etch the tip, kind of expose the tip of the microneedle with good accuracy. And we also coated the microneedle tip, gold-coated microneedle tip with platinum black with nanoporous, which can reduce the impedance by a few orders of magnitude, making it more suitable for electrophysiological recording. And we also studied the stretchability of these microneedle electrode arrays using finite element analysis. It shows that actually when we stretch to large deformation, it's the polyimide layer that is going to fracture first before gold. And the stretchability, depending on the specific designs, ranges from 60% to 90%. And our microneedle modulus is close to 10 gigapascal. It's rigid enough to avoid buckling during insertion into tissues, but also soft enough to kind of minimize the mechanical mismatch to reduce the tissue damage. And for demonstrations, we showed that we can basically place these stretchable microneedle electrodes onto deformable muscle tissues. In this case, we chose the buccal mass, which is the mouth of aplysia or a cyst log. We are interested in this specific marine animal because it has 3D muscle architectures in its mouth. So we are interested in using intramuscular EMG to understand how different muscle groups activate to generate different actions such as chewing, swallowing. So we can insert our microneedle electrodes into different muscle group at different depths. And then when the buccal mass contracts, we can detect which muscle group activates first, and then which muscle group activates last. So with this spatial temporal measurement of intramuscular EMG signals, we can better understand how different muscle groups act synergistically to generate different actions. As shown here, you see that some microneedle electrodes capture stronger intramuscular EMG signals at different stages if we use these microneedle electrodes. If we use a planar microelectrodes, we will only be able to measure surface EMG. You can see from here, the surface EMG signals across different channels are all pretty much the same, which we think is because the EMG signals, when they propagate to the surface of the tissue, maybe they have already kind of degraded and then they kind of affect each other. So with this surface EMG, we will not be able to resolve muscle-specific activities. So this example shows that stretchable microneedle electrodes are a very effective tool for us to study muscle-specific or tissue-specific targeted activities inside the tissue. So this is the first example, and the second example, we show that we can use out-of-plane deformations to make materials stretchable. Here I'm showing two examples of strength sensors. First example is to use origami-inspired design to make rigid materials stretchable. We know a lot of our organs and tissues are highly deformable. And in particular, we're interested in measuring large deformations, for example, of our organs. For example, the bladder. The bladder undergoes extreme deformations as urine accumulates and we empty the bladder. So for us, we are interested in measuring large deformations accurately, meaning that we want to have large strain range, low hysteresis, fast response, and we also want to measure compressive sensing and directional strain responses. So with this, we found that existing strain sensing mechanisms are very hard to achieve all of this simultaneously. So we developed this origami-inspired strain sensor. The idea is very straightforward. We have a pair of electrodes in green and pink, and for each electrode, we have two portions. One portion is the flat portion that's attached to a stretchable substrate, and the other is a straight portion that is at an angle. So we fold this pair of electrodes to form a triangle. We can measure the capacitance between these two pair of electrodes. As you can imagine that as we deform with the stretched substrate, the gap between these two sloped electrodes is going to change, and that changes the capacitance. We compare the analytical models with simulation, which agree pretty well with experiments both. And the way we fabricated this is to use a mechanically guided assembly process. Basically, we pattern each layer using planar microfabrication, and then we attach them to a pre-stretched substrate. Upon buckling, we can form this origami-inspired triangular shape, as you can see here. So the key sensing layer is really the metal layer that forms the capacitive electrodes. And we added glass roll to increase the base capacitance because the size of the capacitors is really small. We also again use stretchable serpentine interconnects to connect this origami-inspired electrodes with external circuits. So you can see here, because this deformation is entirely driven by the folding and unfolding of this triangle, so we can achieve pretty large strain range as long as we choose a large pre-strain. And because the capacitive change is driven entirely by the substrate deformation, there's no mechanical, there's no material change, so we can achieve low hysteresis. And we can also have quick response, strain rate invariant, high resolution strain sensor result. And if we compare the three most important characteristics of strain sensor that we care about, which is the strain range, degree of hysteresis, and the response time, this origami-inspired strain sensor has a pretty good combination of these three. And we can kind of arrange them in different configurations to measure soft material deformation. In this example is a passive soft bar. We can kind of detect its deformation mode based on the strain and the strain sensor signals. So here we haven't really demonstrated the biometric applications, but in a kind of highly related project, we show that, okay, in order to develop strength sensors that are implantable, we also need to solve another challenge, which is encapsulation. So we know commercial implantable devices typically use kind of rigid materials such as metals and metal oxides to achieve hermetic seal, which means that we want the device to prevent penetration of biofluids so that they can operate for a long time, months or even years, decades. So these materials are rigid. If we use soft materials, then soft materials tend to allow penetration or permeation of biofluids into across the material. So there's the fundamental trade-off. Essentially, there are no materials that are stretchable, soft, and have low permeability. So how can we solve this problem? Because if we want to have soft, stretchable, implantable devices to operate for long term in biofluids, we have to find an encapsulation layer that's be able to stretch and also prevent fluid, mostly water permeation. So the strategy we chose was to use existing, a well-established biocompatible material, which is parylene C, which is pretty good kind of barrier property to prevent water penetration. But parylene C is not intrinsically stretchable. So we basically use mechanical buckling again to introduce micro wrinkles into the parylene layer. So we pre-stretch. In this example, we show this stretchable encapsulation using a simple parallel plate capacitor strength sensor. Essentially, we use carbon nanotube as stretchable electrodes, and we pre-stretch the entire stretchable strength sensor, and then we coat it with parylene using a conformal CVD process. And then when we release the sensor, the parylene layer will buckle into microscale wrinkles due to compressive buckling. And you can see here, because the parylene coating process is vapor-based, so the parylene layer can actually diffuse into the silicone layer underneath, forming a very stable and strong adhesion interface. And I think my PowerPoint, okay, it's working. So, but another issue we found is that if we want to have good barrier performance, which means that we want to have low water penetration, we have to use very thick parylene. So one issue of that is that when we release the sensor, instead of forming micro wrinkles, we will have global buckling. So to kind of mitigate this issue, we apply thermal annealing to reduce the parylene modules to make it softer, so we can still form micro wrinkles even for very thick parylene. So this allows us to achieve large stretchability with low water penetration, measured using water vapor transmission rate, shown here. And we show that with this wrinkled parylene encapsulation, we can achieve pretty low water vapor transmission rate. And we demonstrate that this stretchable encapsulation is effective on our soft strength sensor immersed in PBS over 3 weeks. We show that with the encapsulation, we can significantly reduce the swelling of the soft substrate and reduce water penetration into the electrodes. And we show that this is a simple demo. We show that this stretchable strength sensor may be attached to a bladder, and we can use the strength sensing data to predict the volume of a bladder in this ex vivo study. And then the third example, I'm going to show that we can use intrinsically stretchable materials for making stretchable electronics. In this case, with gallium-based liquid metal. Gallium-based liquid metal, especially the eutectic gallium indium liquid metal, has been a very promising materials for stretchable electronics because this gallium indium liquid metal has metallic level electrical conductivity, and it's fluid at room temperature, so it has extreme deformation effectively zero modulus, and has high thermal conductivity, is low vapor pressure, almost doesn't evaporate, is not toxic. So because of these reasons, this eutectic gallium indium liquid metal has been used for different purposes in stretchable electronics. But one challenge that remains is how can we pattern this gallium-based liquid metal at high resolution, because we can't use photolithography to pattern them into micro or nano scale. And the reasons is that this gallium-based liquid metal has extremely large surface tension, almost 10 times of the surface tension of water. This complicates the patterning, as you can see from the previous, the video. It really tends to beat up instead of spreading out into thin films. Also, in ambient air, it forms a skin, which is gallium oxide. This makes it even harder to pattern. So to kind of mitigate this surface tension issue of bulk liquid metal, people have developed different methods to sinter or join individual microparticle or liquid metal particle LMPs. So individual LMPs, they're particles, so surface tension is less of an issue, but they are not really conductive because of the insulating oxide shell. So people have developed different types of sintering techniques to join them together. But these techniques, these processes reduce the patterning kind of resolution. So it remains the significant challenge to pattern liquid metal at micro scale, both in terms of line width and thickness. So what we developed is a method to pattern and join individual liquid metal particles into micro scale thin films for stretchable conductors. So the basic process is that we combine a colloidal assembly process so that we can closely pack and join individual liquid metal particles onto a substrate, which is stamped. We then transfer print the closely packed liquid metal particles from the stamp to our target substrate, which can be flexible, stretchable, such as silicone. So the colloidal step assembly process is a bit unique here, because what we want to achieve is a single layer of liquid metal particle that are closely packed, that are interconnected. So we generate a liquid metal particle colloidal solution using ultrasonication, which is widely used. What we did differently was that we functionalized our liquid metal particle with negative charge, and then we functionalized a substrate with positive charge. So when we insert the substrate into this colloidal solution, the strong electrostatic attraction will closely pack the particle onto the substrate. And when we take it out from the solution, the evaporation process, the surface tension will basically rupture individual liquid metal particle and join them internally. So you can see from the SDM image that we clearly see some joining or welding of liquid metal particles. This is critical to form conductive pathways. And because the self-assembly process is self-limiting, so we can form essentially a single layer or however layers we want by repeating the self-assembly process. We also studied the forces involved in this unusual electrostatically assisted capillary-driven colloidal self-assembly. Due to limited time, I'm going to skip it here. And the key is that if you do just the deep coating, you are not be able to form conductive pathway because of the insufficient surface tension. So I'm going to skip these. And then we combine this self-assembly process with transfer printing, which allows us to pattern this self-assembly layer at micro scale, because we can do lithography using the stamp. So this allows us to form micro scale patterns. We studied how different transfer printing pressure affects the final result, but eventually we can achieve 5 micron resolution, which is actually only a few particles in width. And in thickness, it's a single layer. So the minimum line width and the thickness is both within 5 microns. This is much smaller than what you can achieve using other methods for patterning liquid metal. And because both processes, self-assembly and transfer printing, are scalable, so we can achieve large-scale patterning. And we also studied the stretchability. Liquid metal particles is very interesting. When you stretch, they will undergo morphology changes. So essentially, the resistance change is very small when you stretch such a liquid metal particle thin film. So the conductivity actually increases significantly as you stretch. So in this case, we can achieve over 1200% strength. At the end, it's the substrate that fractures. We couldn't find a more stretchable substrate for these. And we studied how different morphology may affect the final resistance. But you can see the resistance change is really small, much smaller than many other conventional conductors. In this case, we also show that because we have a very thin layer, so it's less sensitive to normal pressure. So we can use this liquid metal particle film to make strength sensors. Strength sensors, in this case, we use integrated interdigital electrode design to make a capacitive strength sensor because it's less sensitive to normal pressure. So this helps us to decouple the influence of normal contact pressure. It can achieve pretty good combination of strain range and hysteresis. And more importantly, because the liquid metal layer is very thin, so we don't have to use very thick microfluidic channels, which in this case, we can make the sensor very thin, soft. Because of the low stiffness, we can integrate this strength sensor onto a very soft, deformable balloon catheter without affecting its intrinsic, mechanical properties. So we can use the strength sensor data to predict the volume of the balloon. And we can also make high-density microelectrode arrays and integrate them onto a balloon. As you can see here, it can undergo extreme deformation. And interestingly, the impedance of the electrode actually decreased as we stretch. It's very different from other conventional conductive materials. We think this is because of the increased conductivity as we deform material. So this is the video which I guess I have to skip. This just shows the inflation of this catheter. And for applications, we use this highly deformable soft balloon catheter for epicardial and endocardial electrogram recording in a dog heart and in human heart. In this case, it's an in vivo study in a dog heart in collaboration with Dr. Igor Efimov at Northwestern University. So we can insert the balloon catheter to form a conformal contact between the electrodes and the epicardial surface of the dog heart. And also we can insert into the interior of the heart. This high deformable catheter is critical to form intimate contact between the electrodes and the complex internal rough textured surfaces of the cardiac tissue. So in this case, we can measure the electrogram signals from the endocardial heart wall, and which matches very well with commercial electrodes. And in this case, we tested endocardial electrogram recording in an explanted human heart, and again, we can not only measure the endocardial electrograms with high resolution, we can also map the propagation direction of these signals because of the large arrays we have. And this is a video showing we are doing endocardial electrogram recording in a beating human heart. And the signals, the key kind of signal characteristics match very well with what we can measure using commercial ECG electrodes from the epicardial surface. So with this, I'd like to conclude by thanking all my lab members who did all the work, and I'd like to thank all the collaborators who made this work possible, and the funding agencies. Thank you everyone for your attention, and happy to take any questions.